Enjoy the session.
Thank you everybody for joining already. I think we'll be kind with everybody for this session to come back after coffee, so we'll give it a minute. Thank you everybody for joining us online as well. There's a question function in your app interface which you can use so we can pick up those questions as well and get them answered by our speakers. So feel free to make use of that and we can interact even a little bit more than, yeah. Our first speaker of this session is Mihail Anton. He comes from the National Bioinformatics Infrastructure in Sweden, and more specifically, the Science for Life Laboratory and Chalmers University of Technology. He will present work that is based on initiatives that have been carried out by the ELIXIR systems biology community, and the title itself is called Open Source Genome Scale Metabolic Models, the Why and the How. Welcome, Mihail. The floor is yours.
All right. Thank you for the kind introduction. I'm in NBIS. I'm also, just to mention, the Deputy Training Coordinator, and that's why you see the little Sweden logo there. Otherwise, as Katarina just said, this is very much embedded in the systems biology community. But we should then ask ourselves, so what's an ELIXIR community? Sorry to kind of, we seem to have a technical difficulty. The slides are not showing up here on the monitor. So I'll just try to continue, but sorry if it's going to be a bit choppy. The ELIXIR community is a special term, and to understand it, we need to think back about how is ELIXIR structured. So I actually copied this slide from the default ELIXIR stack, right? So you see in the center there are 5 platforms that ELIXIR uses, and in order to interact with the scientific community, then it has these communities around it, and you see around the different names of the communities. So what you don't see there right now is the systems biology community. And this is the reason for it. So I'm actually very happy to be amongst the first to talk about this. So the systems biology community is actually, it's been gone through some changes this year. It's had some nice accomplishments. Growing from an emerging focus group, and then an emerging community, and then a community. So this is, in ELIXIR, there's a process for it, obviously. But what it means then for us here is that there's a white paper that is actually going to be published very soon on F1000, which is very nice. And then that will capture the sort of the state of the art, but also the short-term and long-term challenges that we've outlined. And then there's going to be an updated webpage dedicated to this community on ELIXIR. So that's the link there. And last but not least, there will be an implementation study, fingers crossed, right? So I'm not supposed to talk too much about it yet, but I can mention that the idea is that it will start next January. So as I said, I can't talk too much about it, but I did steal or borrow the figure, so you get a feeling for what it is going to contain. So as you see, the core of it is standardization, data, and models, right? And that's going to be connected with capacity building and training, and also with industrial and societal embedding. And there will be 3 focus areas that we want to apply all of these. So metabolism in diseases, in health, and then industrial biotechnology. So with that, we should get back to the main topic of the day, genome chemometabolic models. So what is this? The way I tend to explain it is that it's a network summary of knowledge, where metabolites connect reactions. But what happens in practice is that we start from the genome sequence, and then we look at the coding region and the proteins, and in fact, just at the enzymes, which catalyze reactions. So you have a reaction with reactants and products, and then the products of that reaction become the reactants in the next one. And then you end up with a relatively large network, and you see a visualization of it on the right. So I've used those images from Wikipedia to explain a little bit how these models are created. But even though there are tools that automate this process and algorithms to fix problems, this is not going to be perfect. So what's happening, it's a little bit like this. The model will need curations. The gaps that are left need to be filled, and it's going to require more than a one-time job. So this is something that is kind of noticed already in the community, that there's the curation work is done in iterations. So another problem is that gems are also large. And by large, I mean easily several hundreds of thousands of lines in the smallest file format. That is massive. If we look at the stats, however, it's easily thousands of reactions, metabolites, and genes. So this is a snapshot of some of the open source genome chemometabolic models that we integrate at Metabolic Atlas. And yeah, as you can see, this is not going to be an easy job of maintaining these models. So then what can we do about this? You know, what is there to be done? So we bring these models from the sort of the rough diamonds that they are when they're first created to something that is more like an infrastructure. So the answer is obviously open source, right? It has to be. And this is very much inspired from software development. So, but usually when people think of open source, they think about source code and then releasing the source code. But it's actually more than that, right? It's about the process of maintaining and versioning that source code and having releases. And yeah, anyway, very much practices that are by now standard in software development. But then open source in science is a little bit different. So in addition to what you normally would expect to be answered by an open source approach, there are also some key questions that open source can answer. So these are extracted from the Semantic Foundation for Provenance Management. And the whole point is that every curation that is being done needs to answer some of these questions. And actually open source does, open source does a very good job on answering these, but also it helps a little bit pave the way to making the models more fair. So this means that instead of taking, and this is usually the process, taking a model out of out of the file storage on disk and then zipping it and then attaching it to a submission to a journal, and that never changes. This is a very much different approach. So what is the usual journey to open source? Well, we have to admit it. This is something we're all kind of guilty of. We start versioning files with a naming convention, and then we rename it. That's not the way to do it, but it's a good start. Fair attempt. Then it's very typical that one chooses to use a code versioning tool, typically Git, and then to use a platform like GitHub or GitLab to back up and share the code repositories that are then created. And then once these are in place, then what's happening is that there are a fair of coding conventions, repository conventions. The most obvious one I can think of is including a license. So, and then finally, this culminates into the work being made public. But if you want to fast-track that, and if you would want to bring a little bit more structure to all of these repositories containing models, I'm actually excited to present this public template on GitHub that brings a fair attempt to answer these challenges. So in practice, what it means then for us wanting to adopt or to start an open source repository, you just click a button and then you get to this nice page, very easy form, and that will get you started. Well, that's not the whole story, but it's at least the formal part. Right. So what are I mentioned the 7 questions that start with W, and how does an open source model on, say, GitHub answer these? Well, I've selected here on the left side a reaction or an issue created about the reaction, and on the right side, the subsequent pull request to fix that. So you see that there's a lot of the questions are answered about what is the problem and who does it and when and how. And this is another thing that is not really highlighted, is that this is also a way to engage the public audience, right? So the community at large to report problems and curate the model and then later use it in their work. There's one thing, though, that I would like to highlight. At the bottom on the right side there, it says 2 checks passed. Those are automatic checks. So on GitHub, but also on other platforms, one can include validations that run automatically that make sure that the changes that are introduced pass certain checks. So this is a very important thing that should be leveraged then further on. And then another thing that kind of comes for free when using code versioning and being a little bit open source, one would inevitably create releases for the work. So the models themselves, instead of being named in a way that would reflect the version, now the version is very clearly specified. And I'd like to actually draw your attention to the fact that this model, Human Gem, has had 41 releases. This is extremely atypical. This is sort of the tip of the arrow in terms of open source and model maintenance. But this is something that is very much critical when thinking about models as an infrastructure. Another thing that comes to thought when looking at these different versions is that they ought to have some sort of degree of quality to them. So then testing comes to mind. And I'm very happy to mention this fantastic tool called Memote. It's meant to test genome-scale metabolic models, and it's doing so by looking at the source code and also the annotation of the model, which is very important when integrating data using GEMS. And then another aspect of these models is that they need to be reproducible, in the sense that whatever analysis is being done with them, or in fact, however they are curated, that needs to be reproducible. But here I'm going to mention very nice work from the folks at Biomodels. So they've looked at a fair number of models that they have in the deposition database. These are not only, by the way, not only genome-scale metabolic models, but more models. And about half of them are reproducible, but the other half not so much. So they've already taken steps to bring up a standard for reproducibility and curation of models, which is linked down at the bottom of the slide. And then last, I'm going to showcase a little bit what can one do once the open source GEMS are on a easy to access platform online. So this is a bit of code using Cobrexa, which is a relatively new tool in systems biology, and it's a very nice one also. It's written in Julia. And you see there on line 4, using the raw link to the human gem. But in fact, one can easily change that to any version of any branch in that repository, which means that any sort of workflow that you have, any sort of analysis that you want to do, with minimal effort can be changed to use a specific version and a specific, even a testing version of the model. So then this kind of brings to mind what would happen then if we run these tests and these workflows on all versions, right? So that's a very interesting aspect that hasn't been looked at before. So I'd very much then like to thank the community leads for pulling this off, bringing us from the focus group to a community now in ELIXIR, and also to Katharina, our community coordinator. And the emails are there, and mine as well. So please join the systems biology community. Thank you.
Thank you very much, Mihail. Do we have any questions in the audience? Well, maybe this was all very clear, and everybody knows that you will be around, so there will be time for conversations afterwards. Thank you very much again, Mihail.
Thank you.
We move on to our next speaker in the session, and I would like to welcome Ismini Balsavia on stage. She works at the University of Crete and will be talking to us about genome-wide metabolic annotation for Methanokaldococcus yanashi, which is the first member of the archaea to be sequenced a quarter of a century ago. I'm very curious to hear some of the details, and the floor is yours.
Hello. I'm a PhD candidate at the School of Medicine in Crete, and also an research associate at the BCPL lab at CERT Thessaloniki, Greece, also, as well. So our team at the BCPL laboratory comprises of our PI, Christos Ozounis, professor, and Christos Karapeperis, a pre-doctoral fellow, Anastasia Kasapi, Dimitrios Vasiliou, and myself and another trainee we have in our team. So, this work is about Methanokaldococcus yanashi. Taxonomically, this organism is an archaeon, and we have the discovery of the archaea in 1977, and the isolation of this organism from its white smoky chimney in the East Pacific rise in 1983 at a depth of 2,600 meters. Later, in 1996, we have the complete genome sequence available for this organism. So, it is an autotrophic organism, and it is characterized as a hyperthermophile, obligate anaerobic methanogen. It is an extremophile, as it can grow in high pressures, above 200 atmospheres, and at a temperature range between 48 and 94 degrees Celsius. We tried to annotate its metabolic reconstruction, which is the prediction of metabolic reactions from genome sequences. There are reference knowledge-based systems that associate functional features of gene with reactions and pathways, such as KEGG and biopsych. Biopsych is a collection of pathway genome databases, and these are available in 3 tiers, depending on manual efforts and how often they are updated. So we have tier 1 with extensive reviews and continuously updates. We have tier 2, which are generated computationally, but have undergone some amounts of review and updating. And lastly, tier 3, which are computationally generated without any review or updates. So we have here a metabolic map of Methanococcus jannasi. We can see compounds and reactions in pathways. And in the right hand, we can see compounds and reactions not included in any pathway. So the question is, why do we want to annotate the metabolic map from jannasi? Because it possesses adaptations to extreme environmental conditions, as we have seen. And this will give us insight on archaeal metabolism and evolution as well. And a well-annotated metabolic complement of jannasi will facilitate structural and functional comparative analysis within and across the archaea. So, we had some data available to proceed to our review, and that was a metabolic reconstruction computationally generated in 2004 by Choka et al. And this review assigned 436 enzymatic activity enzymatic activity to 436 gene products. And this database is not available anymore, but annotations are available through other databases such as UniProt, PFAM, or KEGG. Currently, a tier 3 pathway genome database is available through BioPsych, and this metabolic reconstruction predicted 429 enzymes. Now we are at the stage of a genome-wide curated PGDP, and this work predicted approximately 600 gene products with enzymatic activity. So, how we did it? We took those 2 reconstructions, the one from 2004 and the automated from 2021, and we compared all available descriptions for each protein coding gene. If a conflict was present, we searched further for sequence similarity and utilized other metadata from the corresponding records in UniProt, PFAM, KEGG, and elsewhere. When these comparisons ended, we proceeded to a full genome clustering to confirm consistency amongst paralogous genes. And lastly, exhaustive literature review followed to enrich existing annotations. The rationale of our approach was to give priority to non-hypothetical proteins, and that is because approximately the 40% of the genome is specific either to jannasi or to the archaeal domain. So this fact makes reviewing and annotation really challenging. We tried to pay attention for protein sequences likely to be assigned to an enzyme commission number because that would impact the qualification as candidate enzymes. Also, we had cases deemed as critical as they were involved in, they are involved in methanogenesis, or we had multiple paralogs, and those cases were examined thoroughly. We had reverse sequence search against the full genome, so as to detect the highest similarity protein coding gene in the case of multiple paralogs. And in the case of methanogenesis enzymes, we utilized annotations from other databases to find clues. So, to maintain attention to detail, we followed a buddy system, so we had at least 2 persons making changes each time. We had multiple and regular sessions within the last year, and we tried to focus on precision rather than coverage so as to complete our review in a reasonable time frame. So the results of this review is that we have 1,249 protein coding genes, and we had 159 genes updated at the functional description level, and that is almost the 13% of the functionally assigned proteins. Those who are not updated functionally, from those we had 281 that are assigned a more precise EC number. And as I said before, we had 602 enzymes predicted. So this is almost the 30% of the protein coding genome entries. And we have citations that support this evidence for 163 cases. That's almost the 10% of the entire genome. Still, we have 550 cases of unknown function. Concluding, I would like to mention that focusing on precision is an approach we must follow, because non-assigning a function to a gene product has less impact on metabolic reconstruction than assigning a false function. So, in all, we have a collection which is the latest high-quality metabolic reconstruction of Methanococcus jonasi, and this will play a pivotal role in understanding archaeal metabolism, and also it could be available to the wider scientific community for research and development efforts in methanogen biology. These people contributed to our review, and it's Stamoulos, Giavaras, and Dermaris from the School of Informatics of the Aristotle University of Thessaloniki, Ioannis Iliopoulos from the University of Crete, Kaspi and Peter Karp from the SRI Institute, Nikos Kirpidis from the JGI, and of course, Professor Ouzounis. Thank you very much.
Thank you very much. And this is just one really great example of the work that is going on in our different institutions across ELIXIR and how it links to one of the communities. Do we have any questions in the room? Well, then I will, I think, move on. Thank you very much again. And I'm happy to now move on to our third speaker of the session, Nuria Kerel-Rosinach, join us on stage as well. She's part of the rare diseases community and also going to be talking, well, not also. She has been very active in all those activities in the past. She currently works at the Leiden University and will be talking about rare disease-specific fair maturity indicators, which are all topics that are very close to the heart of many of the ELIXIR activities. Let's see, the slides are here. There's also already a mention of the European Joint Program on Rare Diseases. I'm sure she'll mention this later on as well. Enjoy, and the floor is yours.
Thank you very much, Katarina. Thank you very much, Katarina. Thank you all for joining this session. And also, I'm a bit nervous, and it's a bit weird because I usually attend the Festival of Cinema Fantastic of Sitges, and usually I'm there and not here, and it's a bit weird to be here. So, but it's awesome. So I'm going to talk a lot about rare diseases and FAIR. But first, I would like that you put yourself in the situation that you go to visit your health provider, and you are not feeling well, and your clinical profile and your molecular profile is just rare, and the medical doctor cannot diagnose what is going on with you. So you have a problem, and and the medical doctor has a problem, and scientists have a problem here. And what you would like, and everybody wants, is to have all the resources available for all other rare cases, timely, and gather all this information to unveil what is going on with you. Actually, this is the reason why there is this global effort to make your data resources fair. But how to apply these FAIR principles to comply within your community and to be able to explore all this data together. So, in fact, the rare disease community is a big pusher. The rare disease patient organizations are doing for years great effort on driving this and pushing this. But it's not only a problem within the rare disease community, it's also for any community like the ones that ELIXIR also support. Deep diving a bit more about inside the challenges of the rare disease community, the problem that I just explained it has a name. It's called the patient journey, and in rare diseases, usually on average, it takes the patient to have a diagnosis an average of 5 years, and more than encounters with more than seven specialists. Even the cases are rare. What is a rare? I'm going to give a definition of what is a rare disease. There are several definitions, but in Europe, a rare disease is one that is prevalent in one person from out of 2,000 people. So even the cases are rare, the patients are numerous. In fact, the 7% of the population, the global population, the population in the world, suffer a rare disease. So it's a huge problem. And from all these people, only the half part is actually diagnosed. And we only have treatments, known treatments, for 5% of this community. So this IRDIC, or the International Rare Disease Research Consortium, has posed goals for 2027 to provide an accurate diagnosis and available therapy within 1 year of the first encounter to the medical doctor. In these goals, ELIXIR, rare disease community, mainly led by Anna Rath from Orphanet, Sergi Beltran. I'm pointing. Is there a laser? Yeah. Yeah. These people here are the leads of the ELIXIR rare disease community. Anna Rath from Orphanet, Sergi Beltran from SENAC, and Marco Rus, that is my boss, from the Biosemantics Group in Leiden. Align with these goals and want to support IRDIC, providing bioinformatic research infrastructure. So how to verify relevant representative rare disease resources? So what are those relevant resources for research on diagnosis, but also prognosis and drug development? Patient registries are key. all this information on health data on rare disease patients, but also, very important, the standards that the community already have, and also all these knowledge resources for analytics, for enabling innovative research. So I'm highlighting patient registries because they are the first that have been having a focus on applying the FAIR principles. The challenges on this kind of data is that they help with sensitive data, that this data is very scarce and distributed, and very heterogeneous the level of language, data formats, and so on. So the European Joint Programme of Rare Diseases, the EGPRD, is the largest European project on rare diseases that is trying to enable this federated discovery, and is applying a big effort on, is a driver project actually, on applying these FAIR principles on this representative and relevant for research rare disease resources that I'm highlighting. These are the targets in the EGPRD, from clinical to preclinical to research resources. Also emphasize that within the EGPRD, there are all the ERNs, the European Reference Networks of Rare Diseases involved, so all the patient registries of rare diseases, and also more than 35 countries are involved. And importantly also, ELIXIR as a partner in order to help to provide all this infrastructure for making the verification happen. So our approach on verifying rare disease data resources in the EGPRD, we follow the workflow that I'm showing here, and is an iterative workflow because we incrementally make data more fair, and this workflow was described in this paper. In this paper. Led by Rajaram and Anika in our group, and it's composed mainly for the pre-verification parts, the verification per se, and then an important last step that's in the post-verification, that is the assessment of how fair, how mature is your data resource at level of fair. And this fair assessment and of the fair status of your resource can guide fair stewards and data stewards in the next cycle of next iteration of verification, and what are the points that you have to bring some focus or more attention. So in this fair assessment part, what we already have are these fair maturity indicators, or some years ago were called fair metrics, that helped to measure the fair status of your resource. Currently, we have a metric for every fair principle, every one of the 15 principles, and they are universal and described openly on GitHub. And also importantly, there are tools. The way to do assessment can be manual, can be semi-automatic, and can be automatic. Automatic is more machine-focused and is more objective and systematic, and we already have some tools developed by the community and offered as a web service for this automatic assessment. So the question is, how to apply this within a community. So our hypothesis was to use the already fair implementations that the rare disease community are applying for verification. So here, the research question that we want to answer with this project that we performed was, can the rare disease fair implementation decisions in the community be used to assess, to evaluate if your resource complies with the FAIR criteria within the community? So the main goal is to answer this question, but also to provide infrastructure, of course, and a roadmap for adoption. And I'm gonna, excuse me, drink some water. And our approach is for the rare disease specific community to identify what are the implementations that they are already applying, define them as metrics, as maturity indicators, and use them for fair evaluation. So first, to identify the rare disease specific implementations, within the EGPRD, there is this FAIR stewardship programs that FAIR stewards that I'm just putting here some faces like Annika, Niru, Clemence, Cesar, and Bruna, but there are a few more. And in collaboration with ERNs, or patient registry stewards, are working on verifying their patient registries. So we held several content-a-thons that we called within the EGPRD to identify the implementations that the EGPRD community is already applying. And we listed it, and we ranked them based on several parameters, I'm showing here the top that has more priority but they are more in the that were held in the content-a-thon. Next, what we did was organize an open hackathon embedded in the SWAT4LS, or Semantic Web and Application and Tools for Healthcare and Life Sciences. And we provide a project, a pitch, to implement these FAIR implementations that we detected in the content-a-thon in a tool for automatic FAIR assessment. Here on the left, I'm showing the pitch that was open for the community to join, and with the reduced list of implementations that we already prioritized in the content-a-thon. So within the hackathon, join as FAIR evaluator developers from the FAIR evaluation services, Mark, and also Vincent from Fair Enough tool, and also Rajaram as a FAIR software engineer and FAIR expert, and Cesar as a FAIR expert and FAIR steward. So for the global metrics, what the committee did was to apply these metrics, assign these metrics to a FAIR principle. In this case, I'm showing as example F4, findability 4, to your resource to be findable in engine services. And then do a description of your metrics, like a description, what is the test input that you have to provide to the tool, and the conditions for the test to fail or pass. And then implement this defined test in a web service. In our case, we choose the FAIR evaluation services because it's one of the most mature ones. And we did this, we implemented as a proof of concept of our approach 3 different metrics, 1 for findability and 2 for reusability. So in findability, we define to find data resources in rare disease-specific search engines. For R1 to 3 is for community-specific implementations. We chose the emerging one in EGPRD to provide your metadata as a DCAT-based model. And then also we implemented the reusability one, testing if your resource is using recognized by IRDIC already rare disease community standards that in that case were ORDO, the Orphanet Rare Disease Ontology, and HPO, the Human Phenotype Ontology. So this is openly available on GitHub. And next, what we did was organize a training workshop held with people that are developing in ELIXIR training resources like Claudia Carta, Marco, Nabel from a Duchenne patient registry group, Rajaram again as a FAIR expert, volunteers, and also with knowledge on training and applying FAIR principles, like Andra, and Mark from Orphanet, also a FAIR expert on the Orphanet Rare Disease Resource, and FAIR expert as well. So we explained to the community who joined the workshop, the rare disease stakeholders that joined the workshop, how to use these services for FAIR evaluation of the rare disease-specific evaluation of their resources. And we did this with several resources, with patient registries, VASCA for vascular ones, Duchenne and Orphanet, registries already listed in Orphanet, preclinical ones from this human pluripotent cell stem cell registry, Cellosaurus for cell lines, and research like using Wikipathway or Nextprot, renowned resources for discovery, and very used in rare disease fields as well. So we implemented the metrics in the FAIR evaluation services, but also we registered all as a collection that is called ELIXIR Rare Disease something, I don't remember now, but you can go to run a test, you can go on the collections part of the frame, and just select run a test, and here select the type of test that you want to run, or a global one, or this ELIXIR rare disease specific one. And you put your input, your URI input, and we did this. We had this experience in this workshop, and also an idea that came up was discussing how to apply, best apply FAIR, how best to support rare disease stakeholders was from the Duchenne Patient Academy experience, was to maybe organize or start a FAIR Academy to support all this. So. Next, what we did was to set an evaluation protocol for the rare disease community. We call it hierarchical testing because what we propose is to first, because as I mentioned, the verification process that we held is an iterative one. So in the first iterations, we applied the global FAIR metrics, just to be sure that we are complying with FAIR at the universal level. But then we understand the rare disease-specific FAIR metrics as specializations of the general ones. So in next iterations, we apply this to see how able we are to comply with our rare disease with other rare disease resources. So in that way, the aim is to ensure that domain implementations don't replace general implementations. Last but not least, we propose a strategy for IRDIC recognition of these rare disease FAIR maturity indicators. IRDIC, as an authoritative organization, can help a lot to support this community adoption. So we propose to for IRDIC to set a task force to enable to come together key rare disease communities and initiatives and propose a procedure for recognition of the fair implementation choices that the community is already doing. Next, to identify these implementations, and last, to define these metrics implemented into tools and establish an evaluation protocol, and maybe support for a fair academy. So we provide infrastructure, we provide this list of fair implementations in the community, we provide the tests, the metrics and tests, and the evaluation services, and also we provide this roadmap for adoption. So I want to highlight that the EGPRD has been a driver on this effort, and also it's been useful to perform this openly for everybody in the community can join us in the hackathon. And as I highlight also for adoption, the fair academy idea to support verification within communities. One of the key challenges that remain is how to reach consensus with the community to identify and recognize a fair implementation. This is not trivial. But we set in form of our publications of some community requirements that the community can think of to do that. Also to identify the networks in your community that can help and push and already apply these fair implementations. And also having this application of these metrics and explaining to the community how to do this fair assessment, like we do in the rare disease community with summer schools and so on. So as a conclusion, we answer the question positively that we can use community-specific implementations for fair assessment, and we provide these rare disease-specific maturity indicators, how to define them, how to implement them into the tool, and how to do the adopt and propose how to be adopted by the community. And so here, just like the brief summary of how to apply FAIR principles within a community. So again, first set up the implementations, community-based implementations, then maturity indicators, establish a protocol and a strategy for adoption. And with this little effort, we hope that it can be a step to identify that your rare case is actually gathering all this information together because it's fair, is actually common and found in other rare disease registries, and is actually what you have is actually Duchenne muscular dystrophy. So my acknowledgement to all the people that contributed to this work, Anika, Roger, and Mark, Vincent, Marco, all the GPRD colleagues, the ELIXIR Rare Disease community, and all the volunteers that just come to these open workshops and hackathons. Of course, the ECCB organizers, the LMC, ELIXIR, and EGPRD. And yeah, maybe I'm come for questions if there is one.
Thank you very much, Nuria. We don't have questions online, but maybe we have a question in the room. She's touched on many topics, rare diseases, fear. We have a question.
Yeah, great talk, Nuria. So I've just a question about the use of verification and the tools that you're developing also, not just for the community, but also for private industry, like pharma or biotechs. Are you guys considering to also get in touch with these type of communities to also share these principles in these type of communities? And what is your strategy and long-term plan about it?
Good question. I think it's a good idea. I don't have a clear answer now. I think there is no current strategy, but I do think that is a very good idea that could be a next step to do.
Maybe a follow-up is like, are you also considering to essentially get in touch with these type of communities in the future?
Yeah, it is.
Okay, thank you.
Thank you. Any other comments? Do we have any other questions to anyone else who has presented in this session? Did something come up? Well, then I think since everybody was very well in sticking to time, we have gained 5 minutes, but without further ado, I did want to mention that there's 2 more ELIXIR sessions tomorrow, where one of them will focus on beyond COVID-19 and the European preparedness for infectious disease outbreaks. And there'll be another one where we'll hear about the ELIXIR machine learning efforts that are ongoing at the moment. There's also going to be a presentation around federated EGA and the ELIXIR biodiversity community. We have a booth downstairs. You've already seen a couple of faces and people across ELIXIR. These communities that have presented results are open for anybody who's interested to join as well. So do reach out to us, get in touch, and get involved, and enjoy ECCB. Speak to you all soon.